think it's time to start. So, what the program today? So I merged what we did last time, even though I feel this is very, very unfinished. But as the title of the stream suggests, until I messed it up, let me check the title of the stream. I think I messed it up, maybe? No, I didn't. It just there's... Okay, there was a display bug. So that's good. It's just a display bug. Just checking some stats to see if everything is fine. Everything looks particularly fine. I'm getting distracted. Okay, my point is, so last time, just before I went to holiday, we did a bunch of things about quotients, quotient types, and about making terms have an intrinsic equality despite things being in several times. So I have this sort of rigid casting that we can see here to represent like casting it to a quotient. And so 0 and 0 cast to n mod 2. So that's n over 2n is not the same. These aren't two different terms as far as congruence closure is concerned, and therefore, sorry, this is starting well. So, yeah, as you see, I'm like, I'm already not my best. But have a bunch of tea and we'll see how long that will hold me. Apparently it's leaking too. Warm. Anyway, 0, 0 in 0 as seen as a member of n over 2n are two different objects. So congruence closure doesn't see them as the same thing, and they will consider different equalities on them. This way, equality is defined fairly no, not fairly. It's just defined intrinsically on objects, and it just works. And congruence closure can work, despite the fact that we have this sort of fluid terms. But we discovered last time that first, it's pretty hard to make a good type checking algorithm. So I need to clean up some stuff for this sort of thing. Maybe, and also that sometimes we are stuck with 0 seen as a member of n, and as it happens, this is a trivial construction because that's 0, but the proof assistant doesn't know how to eliminate this. So I've been thinking about this for the past 2 weeks now. I went back from holiday and I didn't really find a good way to progress. I also haven't found a good way to do this. At least, well, for all intros is not too hard, but exists intros is a bit harder. So I'm not completely satisfied with this. So this has been done. Is there anything that we haven't done here? Make types more rigid. There is the ID, sort of a term. All refinements will only be a value of time and explicit subtypes. In particular, it's not necessarily an element of curse explicit. May solve the quotient problem. Doesn't equality preserving const-cast, but maybe we need a variant that goes the other way. The idea is it was well tapped when interesting. Okay. To fix the issues outlined in blah. So, oops. Ooh, no, don't do this. Something to explore. is to have casts take both a source type and a return type. That makes me think. I realize that it may cause some interesting issues about type equality. We're far from having a solution. So that's one thing to do. But because I'm a bit stuck, I'm considering, well, I do what I do when I'm stuck. I'm just looking somewhere else until a good ideas come back. So instead of trying to force the issue, which I haven't managed to find a good solution in about 2 weeks, so far, all the issues we've had were solved in about 2 weeks' time. Very often, this is how the secret sauce, this is how the jam is made, is very often I had the idea for the solution like on Thursday or Wednesday, just before the stream. So I get on the stream confident, but really I was not necessarily very confident a day or two before. This time we got to this point where I couldn't really progress this time. And so we're going to do something else. So I'm going to list a couple of distractions and we're going to dive into the one that, the first one. So distraction number 1. Write a supercompilation component for when we have definitions and we want to do proof by reflection. That's how you spell it in English and stuff. I mean, like, you know, the goal of, well, one of the goals of this proof assistant is to be compatible with optimization. Oops. We are not envisioning to make a production grade compiler. However, supercompilation is a cheap-ish and fun technique which is going to obscure all programs enough. And to be honest, I've been wanting to write a supercompiler for years. Here you go. That's my entire motivation. Did I need to type it? No, I didn't. But it's a distraction. Another distraction that we can consider is make this proof assistant usable as an LSP server so that we can fork files. I think it may require serious stuff so that we have a reasonable handling of errors. Capable of saying, oh, this is good, the file works, the file doesn't work. I'm not exactly sure. Like currently errors are very notional. I return random, like there's this thing that are supposed to need a subterm to be solved, but they tell me oh, I've got these that works like badly. I need to improve on this. So I need to understand what how to report to have good. Well, it's not really handling, but reporting of errors, because right now it's terrible. Distraction. We could make this proof assistant output files. Probably we want for the first iteration something which doesn't require boilerplate. When the file format, well, not the file format, when the type of term changes, since it changes quite often. Another distraction, I've been considering using a Lisp like syntax for tactics instead of the ad hoc language. Easier to parse, though see later. Easier to syntax highlight. I need to figure, maybe sometimes heavyweight. Although honestly, for tactic scripts, I'd posit it's quite alright. And I need to find a way to parse terms inside Lisp. There's this thing that there's basically two-way where I could have a sort of quoted form, some kind of a special string, and the parser just sees a string, and then I call the parser recursively on this. Or I could have some notion of a term literal. I don't know yet. So these are all distractions. There are probably others that I can have. It's going to be part of my next commit, obviously. I could just make issues of this. That would be honest. But it's too messy to make actual issues. Maybe like some of these to-dos can become issues. I don't know what I want to do with this. Anyway, today, as you might have guessed, this is going to be the supercompilation component. I'm going to make a new file, compile.hs. Yeah, they don't have a namespace. I can just module compile where. So that doesn't do anything. Oops. So we want to change the cabal file to mention compile. Which needs to compile everything twice, and it's not instantaneous because of course it isn't. Like one of the things about the LSP thing is that I may need to have a better understanding of locations, and I don't know if I can get that out of BNFC. So if I can't, I will have to roll another parser, which is going to be fantastically interesting. But these are like good things to do, and they can like keep our mind occupied while we let the good ideas sift. I'm in absolutely no hurry to complete these proof assistants. It takes 2 years. It's going to take 2 years. I don't care. I'd rather take my time and get something I like. I'm still going to publish this with YouTube. And if one day the distractions for this are not enough, I can still go back to this random model generation problem that I had previously, because I did learn some new things about this. Especially I learned how to generate a fairly good approximation of a uniform sample for a model efficiently with a SAT solver. With nothing more than a SAT solver. It's quite exciting. I don't like another time. I'm getting distracted. I'm going to get distracted a lot today. Distracted from my distractions, I guess. Okay, so we've done this. I think that we want the .jcid. I think I want to remove this. Can I just comment it out? It seems to work. Doesn't work. If I remove it. Okay, whatever. It's just, or maybe it's no, that's just list. No, let's just remove it. Oops. It's a bit frustrating how long it takes. Thanks, Haskell, I guess. All good. So what we want to do. So first thing first, I should talk about supercompilation a little. Supercompilation is a compilation method, data type that we have to define. They're multiply recursive. The computations, the computation, for now it's just going to be an empty type. Data value, it's going to be an empty type, and data, I don't know how to call them. Command is the term from so Airline Curium calls it command. Krivin calls it thread. Bolingbroke and Peyton Jones, well, it's tape, whatever you call it, it's kind of the same thing. A command is interact value computation value. The value plays the role of the stack, by the way. So we have something that needs to be computed in face, and that's something that is already computed. Basically, the stack is already computed. for definition, I mean, we can suspend things. It doesn't prevent thunks. And a typical computation is, the most typical is capture the continuation, and that takes a command. Already we can compile. Okay. So to get us started, we need we need a pair of 2 values and unit. And correspondingly here, we need unpair, or maybe case pair of the command. Sorry. So case pair takes a command. So binds 1, binds 2, and case unit. Binds 0. Let's see. I was gonna need more things because we're gonna need to do something for lead binders. It's sort of a bit maybe too powerful lead binder. It captures the entire stack. So we can already define smart constructors like lam takes a computation and returns a computation. That's the lambda abstraction. And what lambda abstraction does is, so we're going to call this E, I suppose. And what it does is, so it does a computation. It starts by case pair. And so like lambda deployments are a bit high. So then you want to run, what do you want to do? Forget. So it's a computation. It's also like lam binds 1, yeah? So what we want to do, there's something like we'll need to shift. Let's we already need some something very convenient. Lift computation. I don't really care. Ooh. Computation. So we want to lift computation E. That means that the X, well, like it's like you just, it's easy to write with like you take U with X for E to mu X, let's call that, how do I call the stack? I'm going to call it, yeah, K, like in the paper. And we do, so E, but we just skip K against K. So that's var 0. Sorry. Oh, sorry. It's not a case pair takes a command. So we need to do interact. Right? And we can do app. So app is a bit easier because U and V 2. Now we need to capture the stack, new K, and so now we have a command, and the command is U, and we run against VK, as it should. So it takes a computation and a value that matters, and returns computation. And app, it's a bit easier to write. It's app of E and K, not K, not E and V. Let's call it T E. Like so funny today. CC of interact E pair VK. Boom. Sorry, it's not. Okay, it's var 0. Okay, so that was tedious. Remembering how to do this is not effortless. That's the extent of my mental agility today. All that is in the paper. If you want, it's called a dissection of L. It's on my webpage. Nice. It's a pretty long paper. It goes into dependent type things at the end that I never really had the time to go into more details with, but that's interesting. It's interesting because the dependently type thing at the end doesn't enjoy subject reduction, but I conjecture that it's still type safe, at least on closed terms. The reason why it doesn't enjoy subject reduction is that sequent calculi have the all commuting conversions, like of the case. And if you know anything about Coq, or like they're not valid. I think it might be valid in Agda, but the pattern matching is quite involved, and this is not really what transpires in the presentation. So maybe another way to do that would be to make the elementary pattern matching more potent. I'm not sure. I never wanted to do these details. Like I had to stop this line of research and just moved on. Anyway, the point is that this is sufficient to have the entire lambda calculus. We haven't used unit, but we kind of need that to just get started. At the end of the stack. Otherwise, we always have a variable. So this is really the minimum thing we can do lambda calculus with it. Okay. So we're gonna cheese them a little. We have all the types here. That's good. So we have this type history. That doesn't sound very economical, but it's a list of commands. And we have terminate, which take we need a temres, data temres, and that's either stop. It's not a very good name, temres. I'm gonna call that shall I, and shall I stop or shall I continue? Returns the history. And so one is if I end the function terminate, history command to shall I terminate HC equals, and we're going to make the silliest possible termination criterion for the moment. If length h is bigger than 100, then stop else continue ch. Boom. Okay, just checking that my JCID was still working. Okay, the memo function I will ignore for the moment. We need a step function. And second, it's like you can always reduce the muse. They're sort of irrelevant. You know. Well, I mean, you could yield code duplication, but we're not doing a production grade compiler, as I was saying. Code duplication is really not what we're bothered about. So we have our termination criterion. We need a step function that we don't takes state and returns maybe a state. The idea is that there's nothing if the term of the evaluation is stuck value or neutral term. The neutral term happens when you try to case in a variable, and the variable is fixed, something like that. So that happens when you go under a lambda, and we'll get there. Step of my state, no, it's not state, it's command. Set of my command is nothing, so this is boring. I said state, but that's still a command. Van Lahoven things in general, lenses originally, I think they are from, well, not long after, I don't know. Were they known in 2014? I don't know. I'm too lazy to check, but I think that it was not known then, and if it was just a curiosity. Now there's this table of Haskell, so of course we would have recognized that. But anyway, also a polygative were fairly new at the time. So polygative f state to f term to state to f term. That's quite literally traversal prime of state term. So that's what is in. I'm not sure they are terms. So let's do command everywhere. I guess we have nested commands, and that's the difference. I think it's the right thing to do. And basically, we don't want any subterms yet. We never want to split. Yeah, we don't do anything with a command. I may want to change this type to include levels. I'm using De Bruyne's. The article is using named variables, and I think that we'll have to record levels one way or another. Maybe they do that in the monad. I don't remember. Oops. The one we have the step function, we can, and the terminate function, we can define reduce. Here's the definition. Ooh, the definition. The reduce function from command to command. Like case step C of. Oh, by the way, right now I have only two thingies in my commands. Here they are. It's just a computation of value. If we want to implement any kind of sharing at all, like the semantics of things is to be shared, we'll have to use a third heap value, just like they have here, I think. Where is it? No, that was the wrong direction. I really don't know how far we're going to go, but I'm sure that with two, I don't intend to finish today. It's going to be a bit hush. Yeah, it was over full. Should be careful not to pour any tea on my keyboard. I have had enough water-based electronic damage in the past few months. It's been a catastrophe. A very watery and sweet tea flavored catastrophe. Still. I don't know how these things go. I had basically never poured any liquid on anything ever before. Well, anything. I poured some on a table, and more than once, like every week of my life. But I mean, like on anything fragile before. And then in the span of a few months, it happened like 3 or 4 times, and like and it just nearly happened a few more. Sort of things like happen all the time. Like I never do X, and this is the sort of thing you regret saying very quickly. Actually, I wonder. I don't know yet. I was wondering if these heap variables would benefit being named. Yeah, we're gonna go with De Bruyne's. It's fine. It's not too hard, really. I mean, we eventually will have to do the entire dance again of defining subterm traversals and maybe in lift and shift and wift and mift. Shifting not too hard. Okay. Okay, I'm going to make a simpler version. So case terminate his state C prime H as the name of stop steep. We just step there, continue H prime to go H prime C prime. I mean, terminate is a very simple function, but whatever. There's just so that's just there are ways to skip a few steps to not call terminate all the time in a way that still ensure termination. Okay. So when we know how to reduce, I think we skipped a bit. Super compile 0. Let's call SC prime there. Takes a history for some reason, a command, and returns so we need our monad. I of A, deriving functor let's be somewhat generous with this. Okay. But it's not going to stay IO just to have an arbitrary monad there. I'm going to need it to be I don't know if I can actually arrange something. It's fine. Okay. So we take it and we say, oh, if case terminate HC of continue H prime, then we use split of, we're going to say supercompile here. H prime on reduce state, interesting. stop. That's quite remarkable. We still supercompile if it's stopped. We just don't reuse. Seems a bit and supercompile for the time being as supercompile 0. Also has the same type. Okay. So we can, for the time being, import data functor identity. Yes, and add identity here. We can define run, takes an MA to an A, and run of muck x equals get identity x. It's run identity, okay. Fantastic. And so we can finally write our compiler, which is, well, it's optimizer. We call it optimize, and it just can take command to a command. And we optimize by running, by doing run of supercompile empty C. Hello, Dexter Fu. Nice to meet you. How are you doing tonight? Or not night if it's not night in your place. Yes. Can I just do this? Okay. That was Pure's error message. I got scared for a moment. So this is the basic backbone of our compiler. Okay. So that's like this. It's probably not going to run. So I need to go to GHCID. Hey, David. My chat is empty. Hey, look at this. This worked. Okay. So we can do optimize. It lights my night up. How are you doing tonight? Salam of lam of var. Sorry. Ooh, I'm lacking something. I can't actually. How did that work? Ha ha ha. Ha 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 ha. I good. I don't know how to return a variable in this language. Can I even do it? Return a variable should be pushed on the stack. So I guess we could always do it can be pushed on the stack, but I don't really know, well, like what to evaluate it against. That is this. It's the same Haskell as the past few months. There's a sort of, some things are purely Haskell-y, but most of the time there's sort of a, it's just like, it looks a lot like OCaml. It's just like the syntax is slightly different. So you write case instead of match, you write of instead of with. You don't have bars here. You write colon instead of colon. You write colon instead of colon. It's pretty syntactic. Types are in the other way round. So you write identity of A for A identity, which in that case is Haskell is very much in the right there. OCaml is ridiculous, but like as Xavier Leroy once put it, it's not his fault. Milner did that, and who is anybody to argue with Milner? So I'm getting sidetracked from my distraction again. Do I need to add return and thunking? Or can I actually like? I said, oh look, I can do lambda calculus for this. Yeah, I can't do the variables. Can I write the identity function? What does the identity function do? It takes a value on the, it just doesn't do anything. So I don't think it does. I don't think I can. Yeah, I'm sidetracked from my being sidetracked. Yeah. So the basic story of today is I don't know how to make progress on the difficult stuff. So instead of trying hard, I'm doing something else entirely. They're probably not anyone that you know, but they're related to people you might know. Well, I guess Krivin you might. He's well known in mathematics. I don't remember what he did. Model theory, probably. Kevin is an ST. Curien as well. Yeah. So that would be Jean-Louis Krivin. And okay, I'm bad with first names. He was my boss at some point. That's shameful. Pierre-Louis Curien. Thank you. So yeah, I'm gonna type the names out. Yeah, I mean, Like all these guys, they all work in the same place in Paris 7. Young, he's retired, so like could be older, but there's a Méliès in that same team, and he's also related to the famous Méliès who made movies. I worked there for a while. Anywho, sorry, that's not the same one, yeah. Okay. So, pushing a variable on the stack. Oh, no, that's easy. Look, is it? Yeah, you capture the stack. So, no, wait. Ah! Yeah, I think I need the I need to be able to return a value to even do anything. You just need to cast a value into a var into a computation in order to do lambda calculus at all. And therefore, we need return that takes a value, and we need case return of x, no, not of x, case return, so that binds 1. Okay, this has freshened me up actually. I guess the frustration brings adrenaline, feeling better. Case return takes a command. So this is all thunk. There's a way to cast. That's sort of very important for lambda calculus in general. So I'm happy with something. Oh yeah, of course it is. Because lambda calculus is all computations. Everything is a computation. But you need values because sort of the idea of call by push value is that everything that is bound by a variable, so let's maybe something a bit different, but everything that is bound by a variable is a normal variable is a value. So right now we decided that we probably would have let with computations in them because that's more natural for a compiler. So they would defer from having a mu. A mu is sort of a let, yeah, but like half of a let. But whatever. I'm getting mu is CC because I'm consistent. So we can do return var1 here to say that this is the first value. We can apply it. We can apply this. Okay. I'm confused. We can apply it to 2 different values. So we can do pair of unit and app again to unit just to check what it simplifies into. Yeah, I need to interact. So I need to interact that against unit. Boom. Ambiguous reference var could be refined. Did I import refined at all? Oh yeah, I see the problem. It's not imported, but it's loaded. So what I'm doing here is an optimizer. So this is my language so far. So that's supposed to be an intermediate representation, and this is sort of the basic bricks. These are the well, like it's 80% of the basic bricks. One of them is annoying to code. I haven't written it yet, but I will need it. This is fairly fixed, except from I need to add one thing here. And these are the part that I can configure completely. Okay. This is fairly unfortunate. The one thing I can do is well, can I call myself sure. I will then not worry. And fine, as it should actually. So there's this lift function that I need to define. So let's so really lift is I think I have good code for lift somewhere here, and I can just leverage this. Yeah. Okay. So we have to do the thing. The unavoidable thing. It's just, that's going to be just pure. How did I call them? Is the real question. That's a bit of boilerplate. The boilerplate is the part about like you have to do substitutions from time to time, and here you go. Not this. I just want to give a similar name because subs. Okay. Okay, so compilation subs. So there's going to take an int to computation. Sorry, this applicatives. Yeah. So that's a bit magic if you don't know what that does. No, not computation. Value, value. Command. So there's like the int is here. Yeah, I was consistent. Absolutely. Computation. The general idea of this is it lets me define a function on computations by simply mapping functions on its immediate subterms. There's one immediate subterm handler per possible types, and that's why, because these three types are mutually recursive, that's what happens. You're gonna need these. And therefore, we go do some pattern matching. So CCFC, we return, so we need do this and like common subs. Kind of need to define these. These are value subs. These are, oops, common subs. Value. Command. Okay. It's capital C, small c. Common subs. Oops, I forgot some things. On computation, on value. No, I need them. Value. No, actually, that's not common subs. That's on computation of C. It's the immediate thing, so I don't need the value. It's not silly C things. I may want to rename them. Okay, so we're going to see a bunch of boring things like this happening. So then we do case pair. So that's a C. There's also an int missing. Of course, there's one. That's level, and this is the same level. Here we do level +2. These are the two binds here. Case unit. Oops, it's supposed to be a case pair, of course. This is very systematic. The only thing that makes it impossible to derive is these so this time we need the value. Oops, this one we need the value. Return v. Let's return. I guess I don't actually need the computation one, and I may never do, but we'll keep it for now. On value, same level. This is quite correct. Okay, value sub. So we can copy this. Var index. Do we need to do something special for this? I'm extremely awake. No, actually. You don't even need the level. We just return the variable itself. Couldn't match expected type computation. Oh yeah, This is quite correct. There's two things too. It could be possible to specify things so that I could derive that, but I don't really have anything to make it handy, so just let's just pay the boilerplate, basically. Okay, so after var, we have a pair of values, uv, let's say. And if we do this, I need on value. My two subterms are values, so I'm good. So what I do is, as a pair, apply to on the value u, and oops, the other one, on value v. So we apply the on value function to two things: we gather, we collect, we move on. Unit, we won't need anything, of course. And finally, case return. So that takes a command. C, we're going to need on command. So that's a case return here. Oh, and let me do that. That's on value at the same level. We don't bind anything. On value, that's on command. That binds 1. There's a mistake here as well. See, that's the dangerous bits. On command C. Okay, so basically this f here is just saying, oh, this is, if there was not the f, the function would only be pure function, and here say, oh, I can gather metadata, I can gather information about all this. This can be a narrowing function, in which case, if there's an error on any subterm, that raises an error, or it could be a state thing that gathers, like, I don't know, the size, whatever. This one is going to be fairly straightforward. So that's an interaction. EV, like this. Oops, we don't need on command, but we do need on value and on computation. And here we're calling interaction. It's not interaction, it's interact. You know, interact. Applied to on computation, same level E, and on value at same level V. We're almost there. That's because I wrote value here, I guess. Yeah. I'm very, very good at this today. Yeah. Okay. Finally, lift computation. I will be able to define this. I need to define the substitutions first, I guess. And for that, I need the map subs underscore version. So Right, there are the simple maps, so you can just define them. I destroyed something I shouldn't have. Okay, so I need to remove this for this computation, for this version. It's the version without levels? No, it isn't. Yeah, it's the version without levels. Whoa. So that's okay. Okay. How are they defined there? I first define term subs underscores. Like this, yeah, okay. I'm surprised that I need these, but you know. Okay. Sorry. No, that's not the right one. Yeah, it is. I'm pretty sure that works. Oops. Okay, that doesn't work. Oh yeah, I need an extra argument, don't I? And I give them 0 every time. Okay. Yeah, because I'm going to ignore them anyway. I could even pass undefine, I guess. Okay, and so, oops. So this ones are non-trivial, but these ones are coerce. I need to find not even maybe. Yeah. computation subs underscore at identity. Course is not in scope. That's this one. Okay. So now we have enough to define substitutions. I think I need this to be inside substitution because that's going to be defined cursorily. But in the meantime, no, it's subst, not subs. Ooh. Oh, it's term because I'm very consistent. Okay. Okay. So we need to substitute in many things. So subst computation takes a list of terms, one for each variable. We'll need something different, not terms of values. We'll need something different for lets because they're not the same kind of thing. Value to computation to computation. I wonder if there's a way. There's probably a way to leverage in this case. Not sure. I'll think about it later. So I still have quite a bit of boilerplate because all of these are binders and we're going to have a bunch of these. We want subs computation. We're going to have lift value, take the value to the value, lift value is undefined. We're going to have lift command, check the command, find. Then we're going to have shift. Take the list of value, to list of value, and shift I can basically copy from the other guy. Right. No, wait. What? No. Oops. As though the substitution is the name of my substitution. Okay. Here. We'll kind of have to take care of all this. Oops. So CC of C, so that's, I need to shift. So that's CC of subst command, shift, subst. C. Here, case pair, 2 levels. I need to shift twice. And the rest I can just like blindly substitute. Subst computation. And that would be subst command, no, subst computation, subst, and that's value, and that's command. That's not subst computation, that's computation map subs underscore. Of course, these two things don't exist yet. So subst value, 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 that's an important one. And then we're going to do subst command, value, command, command. Okay, we're doing well. That we're making very little progress in our direct goal, but it's fine. Yes, okay. Okay, we're good. So on that note, so we have a substitution here. So here it's var I. There's some math to be done, I think. There's going to be an infinite list. I remember there was some subtlety about this. Okay, so if it's variable substitute, we also need to care about the case return C. Where it's a case return again, and we have to subst command. We bind one variable, and that's C. And for the rest, it's pretty much the same as this one, except that's value, and that is value. And I want to call that U and that U. Okay, so now we still have a bunch of errors. We can fill the lifts, I think, is easy. It's I don't even know if I need them. Here we go. And so now, oops. Oh, that's the wrong one. There's 6. Yeah, that's one is needed. We're probably calling into this one is easy anyway. That's just propagate. Okay. On milestone, we have an optimizer that doesn't optimize anything. If I'm not mistaken. Yeah, there's a bunch of CC. It's not simplified in any way or form. Great. Okay. Okay. That actually I'm on the wrong branch. Never mind that. Okay. Okay, this is now saved in the cloud. I'm sitting on my feet and I'm hurting. Okay. Then we can start thinking about making some things better. Step function is fairly easy, I suppose. It's all is this is unfolded, so the lambdas are unfolded, but they don't mean anything. I could give a better show function so that we can see something. So let me try that. Thank you strings. So show e lexical error. Oh, I see. Now I have two shows. That is exactly what I hope. That's not the right one. That's the one I wanted to remove. Okay. We're saying something. I think I want a bit of spacing. Okay, I'm going to print them as De Bruyne for the time being. Oops. Show you. Show v. Yes. Show unit. Show case return C equal mu. That's down arrow, yeah. C. We can remove this one. Okay. We have none of these, but that's fine. We'll have some have pairs. I'm not sure why we see compiled. Oh no, sorry, that's here. Yeah, that looks much better, and we can finish by values. Not a big deal. We don't do this. It's going to be very, very hard to read. Sorry, computation. To read the results. Of course, it's easier for me to work with this particular notation, but CC of C equal mu C dot we're gonna need some of that. I think I'm gonna leave the parentheses for now. I'll see later. Show C. So for case pair of C as well. Oops. Okay, I broke something. There's two variables. Of course, we could also generate names. Unit. Return V equals down arrow V. Oops. Show V. And we need to remove that show. Boom. So we see there's a bunch of mu's and a bunch of this against something. We can probably simplify this. Return value 3, which is this one for some reason? That looks incorrect. No, that's 3 is the fourth one, so of course that's 0, 1, 2, 3. So we're going to see some things are happening. We can simplify quite a bit. And for such a simple expression, we just need to populate our step thing. Ha ha ha. I didn't commit anything because I forgot to commit my additional file. I just committed trivial changes to other files. Wait, what does this one contain? Oh yeah, this one is this is my to-do list. Okay, fair enough. Hello, yeah. Now we have to go to the step function and not always return nothing. So we have some cases like step of interact of CC of C and V. So here we work by substitution equals subst command VC. In a maybe better evaluator, we might work by some sort of explicit substitution thing. In one of the paper by Bolingbroke and Jones, they have this distinction between things that are already evaluated and things that are not, and might kind of show up as well, like as things that point to values and things that actually point to commands. I don't know. So interact again. Next rule. So here we have a ret, return a value, and here we have something that expects a value. So that's, oops, return capital R. That would be a case return C, and again, subst command B C. Just with this, do we have simplifications? Oh yeah. That's already much simpler, yeah? If I remove this, if I add this, boom. But we're not there yet because we can't do beta reduction. So let's go a few more rules. So if I have a pair here, no, sorry, if I have a case pair here, and I have a pair here of U and V, then U, V, C, and sort of the trivial one for case unit, if this is unit. We just return C. And here we say, oh, we return some value, and this is blocked because there's no further thing. So the question is it the right value? Should be the first one of the two. Yeah, it is the right value. Damn, I already made an optimizer. It's not a very good one. It's a good start. We're going to suffer a little when we do proper termination criterion. Down. So here we go. I started to stream 2 hours and like 10 minutes ago, so 2 hours-ish ago. I spent like the first half hour at the very least just talking, and we already have some kind of optimizer. There's a few pieces missing, but in a way we can already we don't do any splitting. So we could start introducing, I should say, CW multiplicative maybe that's our next step. Next step is to add pattern matching and say, yeah, I want something that just does some pattern matching and I want to optimize it. So what would be a good expression that would require pattern matching? Well, I guess I don't quite need this. Maybe I want to optimize under a lambda. Yeah. So basically, what if I do exactly, oops, let me restore my tests. I do, do I need to add, yeah, I need to add it again. I don't know how this works. Like a very simple version, it seems, is to say, and we ignore the depth, but again, we might want to not, and maybe we want to add the integer here at all. Like we might want to maintain the integer throughout the thing. I'm not sure what that means. So just as a reminder, this integer means I'm under yay many lambdas. Oh, yay many binders. So I've got all these binders on top of me that I've traversed, and I can try to remember that binder depth. Anywho, my splitter, it seems that what's suggested is a simple splitter is, say, I take interact, I've got my like computation to be done in my stack. We're going to keep the stack identical. But what we can do is we can do lambda e prime. It's a bit unfortunate, but whatever. E prime v. We apply that to term computation subs underscore. What do we do for commands? Oops, it's split, not splitter. On commands, we call, oh, we forgot f, my opt function. So we optimize commands, and we ignore the rest. So if we find a subcommand, we go and optimize it, and it doesn't type check. This E is missing. Yeah, that's because that's pure here and opt here. Right. Oops. And this is different, which means that it is incorrect. I should here I should see the same thing as here, which raised the question: what the hell did I do wrong? What's wrong about this? So this kind of looks correct though. Same 3, that's the one here. And what is this 0? Oh yeah, that's the rest of the stack. Yeah. Okay. So this one captures this, and it should be substituted properly. What's happening here? Where does that carry here? Oops. Right. So this should just be blocked, and we should be nailing this. This is close to. Well, not really. There's a 0 here. We should stay, I think. So if we optimize it properly, removing this, I expect to see a 0 here and a unit here. Interesting. Well, it could be wrong. Substitution could be wrong, but it's kind of surprising that, well, the other case, I guess I only did closed term substitution. Maybe I don't do shift correctly. I do. Leave value 1. Why is that a variable to begin with? Where does that come from? Debugging is fun. Is this one? It is, isn't it? I see. Maybe actually. Why is that? That's. Yeah, that's the second argument. Yeah. And now it's inbound. Something really wrong happened. I should go there and optimize this. And this is almost the same thing as this other thing that I did, except that there's a 0 instead of the unit. And it goes bonkers. Why is that? Why is that happening? There's no case for variables. When I'm in front of a variable, I should do nothing except reduce whatever, like obviously reduces. So the muse will reduce and stuff will happen. So the 0 goes there and there. It's just a bunch of muse. What we can kind of do is remove some rules. Like, okay, so we can do that, but just reduce the muse for starters. Aha. There's a 0 here, which there should actually. Yeah, that's the absolutely correct term here. Yeah. The problem is, if I add a single rule, then it just breaks up, yeah? Oops. Don't understand. I don't understand. I could count and do one reduction at a time. I have this luxury. Print the intermediate steps. I am miffed. Okay, let's just inspect things. So CV. I get it. I get it. Yeah, that's it. Like I said, oh no, wait, no, that's not true. No, wait. In C, 0 is always that. There's no doubt. So I'm allowed to do this, whatever the free variables are. So no worries about that. The free variables, they can be De Bruyn's, can be like free De Bruyn's. They can be, if there's a 0 here, it will be 1 here. I did the substitution right. So that's correct. And that is most certainly correct. One thing, it works there, so there's no way it's very likely not to be. I mean, if I reverse the order of arguments, I'm going to get something nonsensical. I've got this. Oh, no, that was it. yeah. That's because yeah, this is the latest binder and this is the earliest. Of course, they're reversed. That's the second. So this is V, and this is U, and V. This is 0 and this is 1. Yeah, that's stupid. So after spending 2 hours making a complete optimizer, we spent half an hour debugging one line. Okay. Man, that's pretty neat. Okay. I don't know if I can go much further without thinking. It's a bunch of design choices to make. I mean, that's already pretty great. So yeah, we could add, we can add pattern matching. But again, the cool thing about this is, look at this. This, well, I don't need this anymore right now. This handles pattern matching already, though have to be a bit careful when I add in lambdas and stuff, binders, things. And yeah, you might want to do like special cases. Terms was just one whole, and we can make a bunch of things. But we'll have to be a bit careful. That being said, if we start adding pattern matching, and of course this is all rudimentary, if we went to make a real language, we would have not only binary pairs and binary. There's an exclamation mark here. On purpose? It looks like it's on purpose. I have no idea what it means. Yeah. Anyway. Right, we're going to do binary matching, is the point. That's sort of pretty straightforward. Just add like I1 value, I2 of value. There's no value for the false case. And we probably want case what? Case I suppose, takes to command, binds one in both, and we have case void that doesn't return anything. It doesn't take a command at all because it's empty. That's the empty computation. It just never returns anything. Oh, not everything is completely done now. So I need to do show I1 u equal. How did I write them? I'm guessing I wrote them Yoda 1 and Yoda 2. No, just one dot thing. Okay, let's do this. It's fair. One dot plus show u. Same for 2. And that's all on values. Here I need to add 2 cases as well. Show case I C1 C2 equals what is my notation? Okay, so that's a pair of mu of 1 dot, and I want C dot here because there's no variable. And then I add the dot here, I add plus show C1 plus, I want to add a comma, and here I show C2. No, not really, no. Well, I can have it because that's going to happen. And for C2, okay, so that's kind of part of the comma thing. I can do mu 2 dot C dot, okay, and show case void. That doesn't take any argument equals, that's this. We don't really need it immediately, but okay. We need more on this indeed. So here we do case I of C1, C2, and level +1. Oops. C1. C2, and that's case I here. There's one that doesn't require anything, not even the level. E at case void. Cool. Pure case. No, pure E, sorry. We're almost there. Here, want something a bit like this, except instead of pair, we say I1 U I1 on value, same level U, here, 2, 2. Okay, that was pretty fast. We already have an optimizer, but I need a program that's interesting. Well, interesting, that's hard to say that. Find an interesting program on this. We can first add, also have some
combinators. That's not actually the actual supercompiler. Supercompiler starts here. Smart constructors, I guess. We can do a case. It takes 2 computations. It's a value into computation, I guess. Just computation. We can also, oh, case is not a good name. So we take a value, branch 1, branch 2. So we're going to start. We're going to start with CC or interact. And here we're going to have V. Sorry. Pair V and var0 as always. That's often anyway. And here we want case E, case I of C1 of like actually lift. These are computations, sorry. How do I do this? Right, actually what I wrote is incorrect, I think. I don't need var0 here. So that's actually V. What I need is case I, sorry, of interact C1 var0 and interact C2 should be E1 and E2 really. Otherwise this is just confusing. E1, E2, E1, E2, var0. No! What is this? The parentheses are not well matched. Okay, that's quite significantly better. Okay, so now we can construct something. So we could start unit as always can do lam. We can do case of var0. We can take these 2 examples. Oops. Parse errors. That's good. That's not good. Oh, that's good. This is just one case, so that's what I expect. Yes, yes. I don't know why there's a bug then. Oh, let's okay. Okay, colon 160. Okay, let's bring this. Actually, it's here. Where is there? Oh, I know. That's the case I, right? That was just silly. I was looking at something completely different. I'm confused. Is that really what I'm supposed to read? Oh, that's the let, I guess. Oops. Okay. Okay. That was a bit silly. Yes, that's compiled var. Boom. So there's a lambda and then there's a case. In this case, I get this and this again. No, wait, that's not correct. Oh yeah, this but under and this one, yeah. But with a second 0, and then there's a. Why is there a third 0? Not entirely sure. That's this one. No, I'm not. This one is correct. This is what I expect, and here. First, there's an issue in my show function. It's going to be more readable that way. Okay, the second is something like this. It's against the 0. Yeah, I think it's quite correct. It is, yeah. Right. That's actually pretty decent. But there's a couple of things that we might want to do to improve on this right away. Which is to look into the stack. So sometimes here the stack is always very simple. As it happens, we when we get stuck, we have unit on the stack or 0 on the stack. But what if this could commute and simplify it inside can that actually happen? I think it automatically happens because of the semantics of pattern matching.
It was. I'm trying to find a situation where we would be stuck on the stack. There's a case of a variable, and I return functions, and I pass this to functions. But that, no, that would. I'm pretty sure that works already. We can try. So something with a free variable. I should just give myself some kind of some kind of symbols like in a. Let's do this. Actually, it's a bit annoying. Some things I just use as symbols. So let's use symbols. The symbols value, you can't do anything with it. Let's say that. They're just you know. And we're going to employ show sim s equals like in scheme we're gonna do colon symbol or something, or maybe not in scheme but in many Lisps. Here not computation value subs. Okay, and so we can replace a bunch of things. So here we can say so here we see first. Can do that again here. Actually, you can just call them A and B. Here is an A. Oops. Ah! I think my keyboard is telling me that it's about time to go to sleep. Let's do a bit more. Let's call this one C actually, and this one D. That D's ambiguate quite a bit. Okay. So my question is, if I start writing something like this,
interact. So I can just write that as a term. So app. I guess we can do case here. Case I 1, 2, 3 app unit. I could give it a name as well because that's just my end of stack. But since there's just the one, it's fair enough to call it unit. Let's say this is belongs to a symbol. Could be a variable, but I can use symbol. So symbol X for the blocking one, and no, it's not app unit. Sorry, unit is here, and we're going to apply that to B. Like, well, we can call it A. This is my first one, and in one case, there's going to be lam. And return compiler var 0. And here we're going to say lam as well. This one we'll just ignore it. So we're going to return sim b. Not in scope compiler.var. It's compile. Yeah, that's because it should be sim. Oops. And yeah, it simplifies. There's very little to do because the stack is always there's nothing to look at the stack for. So there's really the amount of what I can do tonight. Support for case analysis. Let me just this. Oops. Just want to reword these two to add supercompiler. Oops. Ooh. Interesting. The next step is to add lead binding and recursion, so as to be able to do some crazy-ish optimization, like, you know, do something about deforestation. What exactly? Just some, I don't know, is the point. I need to think about this a little because, well, actually, because what? I'm not sure. The point is, this is a call by value semantics or a call by push value. This is very similar. And you can encode call by name computations in them. And like one of the goals that you might have is to, if you do call by name, if you do the call by name interpretation in it, you would have similar optimization than in the paper, the Bolingbroke and Jones paper. So you could do be able to do some deforestation at the very least. But I don't know, if we're lucky, we can even do some call by value stuff. Call by value optimizations are
reliant on a number of things. And like the precise semantics of call by push value might depend on whether you allow your computations to have effects or not. If you do, you can't really have a call by need semantics. You have to be a bit more careful about how you reduce, maybe. I guess sort of, yeah. So when we add this led binder, there's a lot of things that are going on. So what I intend to do for next time, to prepare for next time, is to revisit the sequent calculus as an intermediate language paper, which I think is Luke Moore, Zin Ariola, and Simon Payton-Jones, and maybe a couple others. Paper from like 3 years ago-ish. It's just before the joint point paper, the compiling without continuation paper, which is sort of the idea of the compiling without continuation paper is, okay, let's took the good idea from this sequent calculus thing, but try to shoehorn them in a natural deduction calculus. And that gives the joint points that are currently in GAC core, which is an interesting subject. If you want to know about this, there's a very, very good talk by Simon Payton-Jones at Haskell Exchange 2018. I think it's 2018. No. That must be 2017. Anyway, you look at Simon Payton-Jones on the Skills Matter website, you will find the Skillcast, they are so called, on compiling without continuation, and that would give you a nice introduction of joint points and what's really neat about them and what's absolutely horrible about them, because it has its dark corners. I got hit by it quite a bit. I'm going to be rambling for half an hour if I don't stop there, so I'm going to cut stream. I want, as always, to thank everyone that has been watching part of the entirety of the broadcast. I hope you enjoyed it. And yeah, I'm going to go to bed, so I'm going to cut stream now. And until next time, don't forget to stay curious. Cheers.